Professor Shiga was kind enough to look at the calculations and noted I'd made a wee bit of a mistake or wasn't quite right. I'd forgotten about it 20 years ago. But to determine the offset mass, but we put it offset that time at 1 kilometer anyway, because if you looked at a tire, you only have a small amount of on the outside, or big be really close to the center of rotation. And as the African plain is some 8 kilometers above the Pacific Ocean, the idea was we've now put, and everything is shedding from Africa. Look, there from Jurassic, South America going west, Australia is still traveling east under the equator, India traveling east before it went AWOL, the whole lot going north. So the center of mass was put offset on the African heavier side by 1 kilometer. It's arbitrary, but it fits in with all the other theories of shifting from the heavier side to the lighter side. So this allowed me to do these two cartoons using Word and paint. I'm quite pleased with them, because who actually is turning the Earth now? And how did the center of mass come to be offset? So the gravitational pull of the sun on the newly created planet created offset center mass, causing it to rotate. When all those bits and pieces came together, were big enough to attract the sun's attention, to stop it flying out of our particular area, it actually had to pull an offset mass on it for it to work, to make it turn. No different to the handle on that quern. It's the sun what done that. It was the sun. And at the same time gave us a tilted axis and balanced it. And after this very day, 4.3 billion years later, we are still rotating on the same axis, north-south. So we started the rotation at the same angle anti-clockwise. This is a bit later, when after all the bits came together and started to zone, the heavier bits gone to the middle, the lighter bits on top. There's the slag on top of the embryonic Earth. The red bits are still bits of magma. Professor Shiga, together with myself, we liken this to a crucible of iron and the slags on top. The slag, he put the minerals for the slag as calcium, magnesium, silicate, all the light materials. The minute they start to move, tectonics was born. So this is my supposition that when the top bit, we are walking on the slag, we are walking on the light components, silica, calcium, magnesium, and the light elements which make up our crustal. This is the planet we walk on. So we're getting there, and the sun's created the outer balance. It's done on every planet to rotate it, much like the handle on the quern. And this allows you to make a diagram to start. There, if you've got a rotating disc either side, it doesn't matter which way you rotate it. There you put an offset center of mass, and the water will go from the heavier to the lighter side. I actually did an experiment for this. I don't know if you can see this, but I all but broke my hands. Here's the lump of offset mass. There's the center. There's the tube full of water, matter in it. And I can tell you that I should have known that anyway, because the minute the Panama Canal was cut and made, it was noted that the Pacific was higher in sea level than both the Atlantic and the Indian. It still is. The NOAA, American Association of Atlantic, put it all down to the fact that the salinity changes. Forget about that explanation. The water went to the lighter side. It swung around to even out. It always does when you cyclone something. And the same reasoning can be applied to the crustal on the Earth. It will slide from the heavier side where the offset mass is to the lighter side. This is a diagrammatic, just to sort of put your thoughts down. And this is just a thought program, nothing else. Divergent margins either side of Africa show that the plates are shedding up to the lighter side. This then becomes something more esoteric. It becomes now a vector diagram from which you can now start to do your calculations. There are variations how you do it. I won't break your head, but we take a little element there of Earth, and there is the force F1 going outwards, and we take it to the center, and there is the principal force F on the circumferential force on the Earth. And we want to turn that into a statement. It starts to look very much like the statement looks like all these forces are not dissimilar to that, which happens when you pump up a sphere, and we've got to calculate that in industry that doesn't bust. So when you get your nitrogen cylinders and your Keller gas, we know that they've all been calculated, it won't break. And from that, we can make a small little diagram for tension and compression. And now stop breaking your heart on that one. And we got a picture in our mind. We've got a picture in our mind of what the vectors look like. So let's now go back to this picture and say we're going to get what F1 is delta F over this angle, this little angle here. We've got the mass, the radius. So let's just put this all into here. Mass of the radius is of the crust is 2.6 kilograms. The radius is 6,400 kilometers. Eccentricity is 1 kilometer. The velocity you have to put in radians because it's rotating. And you put all of these figures, and what we're looking for is the total force at point X. We are looking for this force, and not that one. We're looking at this force. And so we start to integrate delta F equals the F sine theta, and the total vertical force, after you summate it all the way around that circle, the Earth, comes out at mass of that unit crust. We took the element times the radius of the Earth, which is 6,400, the rotational speed squared, the radius of eccentricity, the offset of the mass, center of mass, pi over 4. This is the first time an equation has been given to explain the forces on the surface of the Earth. It's in no other textbook, and I claim the first of this. This was done in 2001. It still had problems. To make it easier to the non-mathematical, I've just done this diagram. It's not 100% correct, but it's good enough. There's your center of rotation. There's where your mass is concentrated. It's been pulled out by the sun that it can rotate the Earth. And I'm looking for the circumferential stresses that will break the surface in half and move it around and give us the topography we today enjoy and our recycling planet. So hopefully you can see it from this. It's all that maths is just to show that. Now we've taken Dr. John Crocker, the late Dr. John Crocker. I gave this work to ask him his opinion. He was in our club and also secretary of the GA, and we became very close friends. Sadly, no more, he's gone. And he did approach the problem with an entirely different set of vector diagrams that come out with the same answers I had, which cheered me. And that allowed me to make a simplified diagram. There's the rim in tension of the Earth, the force, there's in compression. So we've got the splitting of the South America, Australia, India, this side, that going east, this going west, and all of it meeting up in the Pacific. There's the India coming to the Pacific, and the other side, Australia coming in from the side, North America, Asia moving slowly but surely into the Pacific. So we've got a diagram showing the magnitude of the forces with these offsets of 1 kilometer and the Earth's rotational velocity. The heavier side is in tension, the lighter side. You see that all the time. We see that in a limiting case, if these two were together, then everything would be balanced. But now is the exciting part. We now put into the equation the actual dimensions we used in the vector diagram. The element of crust, the kilometer thick by 1 meter by 1 meter, always easiest to work in with one. You can always multiply it by the actual number later. The average density is 2.8 kilogram per meter cubed. Therefore, you can work out the weight of that element. The radius we know is 6,400 kilometers. rotational speed in rads per second, 7.27. And we put it all in this equation. And bingo, we come out with a force. The circumferential tensile stress is 0.00744 times meter per millimeter squared, or to those of us who know indices, 7.44 times 10 to the minus 2, which is the same as 3/4 of the atmosphere above us. And as I was brought up in imperial circumstances, I've come back to pounds, feet, inches, and pints. It comes down to 10.8 pounds per square inch. Well, what is 10.8 pounds per square inch? It's a flat tire, a very flat tire, but it's 100 times stronger, more powerful than the basalt, the tensile strength of the basalt in the oceanic and lithosphere and the mantle, which has a proven tensile strength on the lab benches between 0.08 and 0.14. So 10.8 is nearly 100 times greater than the circumferential force. It'll have no trouble breaking up a supercontinent, no trouble at all. At half a kilometer, it's still enough. At 50 times, so we can still, so it's only need be the core of the Earth need only be out half a kilometer in 6,400.0015%. It's a small difference, but when it's attended to the surface, it's enormous. I sent this off to Professor Howarth, head of mathematical geology at UGCL. At that time, he was also principal editor of the GA, and he did all the whole thing again, but he did it with this route, statistical route. It comes out with the mean circumferential crest is 72 in the first two significant figures. Never mind all that nonsense. And on the crust, 77, average calculating of the two of them was 74, right in between. And Professor Howarth went to enormous trouble to help me rewrite my paper. But for the life of, we could not get another 4 geologists from the GA or the GSOC who would put their hands and say, yes, Bob is right. He has got a point, because the sun, the Earth is an unbalanced, is a fully balanced, without circumferential forces. But have a look now at what this means to the average person. If you take that value by Howarth, 7.29, and we put it, that force, we put it over a meter by 1.25 meters, which is the rear end of a Mondeo estate car, Vectra, or whatever it is in the Vauxhall range, Toyota, which has got roughly a surface area of 1 meter by 1/3 meter. The force over that, using over every little millimeter, comes out to 94,770 newtons, which is enormous. In imperial units, this equates to a push of 21,300 pounds force, or 9.5 tons. Bring it down to everyday figures, round it up, it equates to this vehicle being pushed by 180 people who weigh 180 pounds or 81 kilos, someone like myself when I was at full strength. The force is there. It's no trouble to split up a supercontinent with the forces of this magnitude. The incline between the Andes, Jackie Gill did this, one of our members did this cartoon for me, as the incline between the height of the Andes taken at 5 kilometers, and this is between the Peru, Chile, Trench, and the Cordillera, taken as 1,000 kilometers. If the actual difference inclination is 1 in 200. In other words, next to nothing. But look at the ramifications of the way we can now mathematically model and get the forces and get a handle on what's actually happening in tectonics, not for some nebulous convection current which we can't measure and don't know where it comes from, but we can now look at this, and we can now, top people have looked at the maths and have accepted it.